So evaluating limits by direct substitution is simply putting the value for the limit in for x and evaluating. So with example 1, question A, we have the limit as x approaches negative 3 of x plus 9 over x minus 3. Now, direct substitution is always a good method to check, even if you know that something else may work, because if direct substitution does work, that's what you should be doing. So what we're going to do is we're just going to take the negative 3, substitute it in for x, and then evaluate. We have 6 over negative 6, which is going to simplify down to negative 1. Example B, we have the limit as x approaches 2 of x cubed minus 3x squared. Exactly the same situation. We're going to substitute in a 2 for x, and we're just going to work it out. So we get negative 4. So now taking a look at example 2, if we were to try direct substitution, we would end up having 5 minus 5 on the bottom of that fraction, which would give us 0. Now, the only time that we have a limit that we can't deal with is when we have a 0 on the bottom. But we do have a couple of tricks that we can pull out. This is the first one. It's by factoring. So we have the limit as x approaches 5 like so. In this situation, take everything that you can factor and factor it as much as possible. What you're going to notice is as I'm going through the steps as well, I'm carrying down the limit as x approaches 5 piece. That has to stay with as long as we still have the limit. Which what that means is until we substitute in the 5, we need to write the limit with. So if I look at the top here, I can factor this into x minus 5 and x minus 1. Bottom is just x minus 5, it doesn't factor. But what we now have is x minus 5's on the top and bottom. We can cancel those out, which leaves us with just the limit of x minus 1. So what we've done by factoring and canceling, we've eliminated that possibility of 0 on the bottom. Now we can go back to direct substitution, and we find that our limit is 4. Example 3 leads us to the next kind of limit strategy. It's just simplifying. As you can see, we've got a couple of brackets there that we can simplify out. We can expand, and that's exactly what we're going to do. So here is our limit. And what I'm going to do, I'm just going to take that first bracket that's cubed, an exponent of 3 means we have that bracket multiplied by itself 3 times. I'm going to take the negative 2 in this bracket, distribute it in, now it's time to start basically foiling. So I'm going to take these first 2 brackets that we have, FOIL them together. So negative 2 times negative 2 is 4. We have negative 2 times h twice, so we have minus 4h. And we have plus h squared. We still have that third bracket of minus 2 plus h. We haven't multiplied that in yet. To simplify the piece at the end a bit, we can add our 4 and 4 together to make 8. So now the multiplication, it's almost like foiling, except it's going to be a step longer. Take every term in the first bracket, multiply it by every term in the second bracket. we have our two terms, the negative 2h plus 8 that was on at the end. When we do a question like this, we're going to get quite a few like terms that will cancel each other out, or will at the very least simplify. So we have a negative 8 and a plus 8. I'm going to write my terms in descending order, highest exponent to lowest exponent. So we start with h cubed. I end up with negative 6h squared and plus 10h. Now, even with all this simplifying, we're still going to end up with a 0 on the bottom. So when we simplify, we also have to look to factor as well. If I look at the top of that fraction, I can take an h out of all three terms, which is going to allow me to cancel with the h on the bottom and eliminate my 0 on the bottom. Now that we've done that, we can jump back to direct substitution one more time, and this limit is 10. The last type of limit strategy we're going to look at is rationalizing. Rationalizing means that we need to eliminate the root sign. Now, in the past, we've only ever cared about rationalizing the denominator of a fraction, not the numerator. We could leave root signs in the numerator. With limits, it doesn't matter where the root sign is. We need to move it from either top to bottom or bottom to top. So we have our limit. And if we were to try direct substitution, we get 0 in both the top and the bottom, which we can't have. So what I'm going to do, in order to rationalize, we need to look at the piece that has the root sign. That would be the numerator in this case. We need to multiply the top and bottom by what's called the conjugate. Now the conjugate is almost exactly the same. It will have root x, it will have 10, but instead of a minus sign, it'll have a plus sign. Conjugates always have the opposite signs. So we'll take the top and bottom, multiply by root x plus 10. We will have to do some foiling. On the top, root x times root x is x. The outsides, 10 times root x is going to give us 10 root x. Insides will give us minus 10 root x. And the lasts will give us minus 100. I'm not going to distribute out, I'm not going to FOIL out the bottom. The bottom was the piece that didn't have the conjugate, so we're going to leave it as two separate factors, and I'm going to explain why in just a minute. So we'll simplify the top. We have the 10 root x's in the middle. That'll cancel each other out. So on the top we get x minus 100, and we have our two brackets on the bottom. So the reason that I didn't FOIL out the bottom is so that we could have something to cancel off with the top. Those are those x minus 100s. So now, by canceling off the top, we have a 1 on top. We have root x plus 10 on the bottom. We've simplified. We've taken out what we can. We go back to direct substitution. Simplify it out, work it out. Square root of 100 is 10. And we get left with 1 over 20.